Hi, I'm Donny Greenberg. I'm the co-founder and CEO of Runhouse. Have you ever thought about how Ray sort of looks like some serverless frameworks? It has a sort of serverless look to it. So on the left here is Modal. It's a popular serverless system. You can see that we decorate a function with the compute that we want it to run on. And on the right, we have Ray, where we also decorate a function with the compute that we want it to run on. The thing is that if you've used Ray, you know that it's doing something completely different here, right? Modal is running outside. This Python code is running outside of the system. I trigger it with a specific CLI command, which packages and deploys it, whereas Ray here is actually using this decorator to dictate how this function should be scheduled within the cluster. So it runs inside of an already constructed cluster. And often when you're bringing Ray to new ML practitioners, they'll ask, well, why do I have to decorate this function with the compute I wanted to run on, and then I also have to fill in a kuberay config which dictates the compute that I want this to run on, which is doing the allocation out of Kubernetes. So for argument's sake, let's say you built Ray for Kubernetes, where you used tasks and actors, but you replaced the Ray cluster with the Kubernetes cluster. And so what I mean by that is that when you use decorators in Ray, you're specifying the compute that a function should run on, but really you're scheduling it on a specific process within a set of nodes. If you take this to the Kubernetes world, those processes, the resources that the actors use are actually full Kubernetes resources, right? Arbitrary resources, a kuberay, Ray cluster, a regular pod, an auto-scaling service, an SPMD set of workers, whatever you want. You can replace the Ray scheduler with the Kubernetes scheduler, which is how you schedule resources on Kubernetes. Replace the Ray autoscaler with the Kubernetes autoscaler, Ray observability with Kubernetes observability, scheduling management, et cetera. So there's this interesting parallel between some of the Ray components and the Kubernetes components if you view it as like the serverless system with an actor and task Pythonic dynamic interface. Things that we don't get for free here are one, like the actual deployment and dispatch and scheduling and distributed logic. That Kubernetes has none of. You don't have log or error propagation or fault tolerance. Those things you have to basically take care of yourself to make such a system usable. And you also don't have Ray's concept of a runtime env where you can patch and update dependencies and control the environment in which the system is running. Really, you'd have to build your own fast image patching system to make this usable on Kubernetes. The interesting thing about this is that by moving this to Kubernetes, you have many more options for the actual compute primitives that the actors and tasks use. So our nodes are no longer only individual processes that get called once. You can have a single machine node, which is a pod if you use Kubernetes, or you could have an SPMD distributed workload, like a PyTorch distributed group of workers. You can have a single controller resource where your actor or task is being put on the head node of a Ray cluster or a Spark cluster and is actually using Ray, let's say itself, to run a Ray program and orchestrate inside of that cluster, but you yourself are interfacing with the actor that does that from the outside. You can have auto-scaling inference services, which is obviously what Kubernetes is good at. Or you can have stateful replicas like sandbox containers, gyms, emulators, things like that. So now our set of primitives that we can work with through our actor framework is actually kind of blown out. And if you think about what this enables, a typical RL workload actually looks pretty similar to this. You've got, let's say, Ray distributed workload doing some data processing. You've got some inference auto-scaling workers that are generating trajectories. You've got some training workers that are maybe traditional SPMD distributed that are actually doing back propagation and generating new sets of weights. Maybe you also have some sandboxes on the side that are doing evals or agentic multi-turn tasks. So if you can orchestrate natively in Python in this way, it actually opens up a world of workloads that you can program natively in Kubernetes. But also, I think it's actually very consistent with emerging patterns of Ray usage, where you want to be able to use multiple clusters in composition, maybe also with other resources, in many types of workloads. For example, you've got offline ML pipelines. You've got that are really deep, have multiple different stages. You want to use this Ray cluster for the data processing, you want to use this one for the training, and you want to be able to compose these things nicely together. Multi-step inference also, often you want to break up into multiple steps. so that you can reuse inference services, or so that you don't have a dependency coupling between the different kind of subservices. And so this pattern of being able to reach out and use Ray clusters on the fly out of Kubernetes is very powerful for just core Ray usage patterns. So another thing that we can change about this is that we can make it remote execution native by taking out the serialization as the way that the tasks are actually farmed out among the workers. So Ray serializes the task or actor logic to be able to send it around, which means that the dependencies on your workers are pretty tightly coupled. Like, you don't really want to have version mismatches between nodes, like Python library version mismatches between nodes in your cluster. If we remove that completely and we make it so that these actors talk to each other strictly over HTTP, well, then we can actually make this remote native where you can actually write a Python program on your laptop that can farm out work to a Ray cluster in your Kubernetes cluster on the fly, and just say, okay, I'm about to run a Ray tune job, or I want to run a data processing job, and I just want to scale it. I want to run this as a Ray program. Please run it on X nodes, or an X amount of compute on Kubernetes, and that's a Ray cluster. And in Python, it's just reaching out and making the HTTP calls, and then actually deploying the logic that you want to run on those nodes, to those nodes on the fly. And so now, you actually don't need to be tunneled or SSH'd into your Ray cluster to use it after you've launched it with KubeRay, which is more of a VM-like regime where you were, like, let's say, launching an EC2 instance and working with it to do your development. Now you can actually use this more in a serverless regime where you write and run your code totally locally, but you can just use remote resources like a supercomputer or like a process pool where you just offload it from your laptop. And what that also means, because now all of this is captured in Python, including your Ray programs, your other programs you're orchestrating, is that like Ray, they run as is in production. So you can take an existing Fast API app, an Argo workload, an Airflow node, whatever is running Python today for you, or your friend's laptop that you want to be able to run the exact same code, and just drop that Python into that environment, and it can now reach out and wield massive compute out of your cluster on the fly without changing anything about its local runtime and without having to reconstruct the code in any way or restructure the code in any way. So we built this system. It's called Kubetorch. It's not PyTorch specific. We use the name Kubetorch in analogy with a particular API that we use, that we model off the PyTorch APIs. We do support decorators, but I'll show you in a second. They're for whatever reason, we're doing something very different from Ray. Ray is really a powerful distributed framework. This is actually more of an orchestration framework, and it actually makes more sense not to use decorators because you don't really want to couple the infrastructure implementations to the code proper, and that's why we use this other API. But essentially, Kubetorch allows you to run Ray programs serverlessly, or in another way, grant your ML practitioners, if you're an infrastructure team, access to powerful compute to launch Ray clusters serverlessly from inside of their local Python programs and then run those in production, in CI, and GitHub Actions, and Argo, et cetera, as is. The basic structure of it is extremely simple. You specify the compute in Python from anywhere. There's no local runtime. There's no special launch command. It runs inside of any Python with standard Kubernetes authentication. You specify the compute that you want your program to run on. In this case, I'm doing something really simple, but you shouldn't see this as abstractive in the way that it limits your capabilities. This is obviously designed to be friendly to practitioners, but you can build arbitrary Kubernetes manifests through this API or use your own manifests. So we're trying not to make it so that by adopting an abstraction, you're actually limiting what you could do if you were just using Kubernetes directly. And then you just specify your program that you want to send to that compute. You get back a local callable that's identical to the original, or if it's a class, you get back an actor. You can deploy scripts and fast API apps or HTTP apps as well. And when you call it, it's actually operating over RPC on the cluster, and it propagates back logs and exceptions as you would expect. So if you think about this in the context of Ray, let's say I have an HPO job, which I want to run deep inside of some Argo workflow. I could either enable Ray within my stack in such a way that I turn my Argo pod, which is already there running, into a Ray cluster, and I migrate over my program to basically be kind of Ray as the outer encompassing layer. Or I just basically take my HPO job, maybe I turn it into a Ray tune job, which you can see here, like, inside of the actual function, which you could, you would otherwise, let's say, wrap, if you were launching it through, let's say, the Ray jobs launcher, you would wrap this in a CLI and you would submit it. I just take that function, which is actually calling Ray init and running the HPO, and I just specify I want to run this on a Ray cluster with such and such compute with such and such image, and I call it normally, and I can just drop this into Argo as is. Something that's really important about what we do is that you can see here I'm specifying this image. Kubetorch only works because we have extremely accelerated packaging and deployment. Basically, if you were to try to do this with Kubernetes directly, it would be extremely slow. Every time you ran your program, you would have to wait for pods to basically get allocated. Maybe you're waiting in a queue, start it up, downloading data, etc. We've made it so that when you request compute out of Kubernetes through Kubetorch, we're essentially bringing the compute to you. They get allocated and we're holding them in place. And as you update your code locally or you update the images that you're working with, those changes are getting hot synced to your remote environment in only a couple seconds. And so you have basically like a native local development experience with very powerful compute. There are several advantages of using Ray serverlessly in this way. One is developer experience. We have a fully remote development experience, fully supported. You can use any IDE. You can run this in notebooks and just grab compute and use it on the fly inside of a notebook. I think everybody here knows that the Ray client is deprecated. If you like the Ray client, this is giving you something similar, but without the serialization problems that led to the Ray client being deprecated. You also don't need to constantly SSH and tunnel into your head nodes. You can just use them on the fly from afar. You have really good fault tolerance because we can actually we give you the ability to catch and handle exceptions from outside of the workload, right? So anything that you're doing through Kubetorch on remote compute is being called over HTTP, so there's no cascading failure. Nodes can fail, the whole thing can fail, you can get CUDA errors, nickel errors, exceptions from inside your application. They'll propagate back to you inside of your single controller Python that's running your Kubetorch job. And it can decide, oh, I just got an I actually want to launch larger compute to redo that. Or, oh, I'm in the middle of a data processing job and I caught an exception. I'm going to just checkpoint where I am right now before I raise that exception back up to my user. And so you can do really, really advanced fault tolerance really simply in Python just because you can actually handle and catch these exceptions, and there's no cascading failure. There's no head node, there's no local runtime, there's no single point of failure in that way. Our dependency isolation is really good. So because we don't serialize code across different workers, you can use completely distinct images at different stages. So if you had, let's say, like a multi-model inference workload, you could have one set of models be an auto-scaling inference service, which is running Triton, and another set of models be VLLM. You don't have to care that they're running different PyTorch versions or whatever, Triton's not running PyTorch. But you don't have to care about PyTorch version mismatches, et cetera. And let's say you're running an RL workload, and in the middle of your trainer, you want to launch some sandboxes and then make some calls into those sandboxes. Who cares that those sandboxes are like CPU-only, chemistry libraries? It doesn't matter, right? They can be completely distinct. We have really good portability, as I mentioned. If your code runs on your laptop, you can just run it in CI. It's a great way if you're an open source maintainer to be able to run CI using heterogeneous or advanced compute without knowing that your CI is going to run in a different way than, let's say, if you had enterprise customers, how they would be able to run it inside their own doors. It's also cloud agnostic, obviously. And then our hardware efficiency and scalability is very good because we give you such fine-grained control over the compute that you're launching. So you have really arbitrary control, the same control that Kubernetes gives you over the way that your services scale, over the specific compute that you launch. You can use labels, node selectors, chains and tolerations, whatever you like. As much control as you have in Kubernetes, you have through Kubetorch. And often when you're trying to resource optimize, you want those really fine-grained control. We can even do crazy things like actually scale up and scale down workloads that are actively running. So if you have like a training job that's running and then some capacity frees up in your cluster, you can actually just scale up that training job to eat the available capacity and it'll just keep on humming. And then let's say inference spikes or somebody needs some compute, you can just scale that training job down and now your cluster just hugs 100% utilization because you have this much richer control over how you utilize compute. And then finally, it makes incremental Ray adoption much easier. It enables incremental Ray adoption. We often see hesitance to adopt Ray in certain teams or scenarios because it feels they think that they'll have to adopt it all or nothing. They'll have to decorate all throughout their code base. They'll have to change their Argo jobs or their Airflow jobs to be Ray clusters. you don't really need to, I mean, everybody here knows you can do these things somewhat efficiently, but the most efficient way you can possibly adopt Ray is inside of an existing program you have to take a function or class you already have and say, oh, actually, I want to use Ray inside of this, and then just run that on a Ray cluster, and the entire rest of your execution locale is completely unaffected. So that's another powerful use case. Kubetorch is open source. If you'd like to collaborate or contribute or just talk about how this would look inside of your own stack, please feel free to reach out to me. My email is donny@run.house. Thanks very much.